Good morning. This lesson is for my Trig-Precalc class, but before I get started, I want to say I hope that everyone's doing all right out there. I'm not sure how I'm going to title this. I'll title it how I title in the title. But what I am sure of are two goals for the day. Our first goal is going to be to create a logarithmic function from an exponential function. Our second goal is going to be to find nice points for the logarithmic function and better understand what the input and output represent. So, with this lesson, I want to do a little bit of review with the exponential function, and then hopefully that helps us better understand its inverse function, which is the logarithmic function. So let's go ahead and jump into our first goal. Let's start with y equals 2 to the power x. One of the nicest exponential functions there can be. We can make a table and graph to see the behavior of this function we are starting with. So I want to know what we're starting with, and hopefully that helps us understand what the inverse is going to do. All right, and I have a table. This is kind of a larger table, but I want to really encourage the following technique when filling out a table. Make the middle value of the table be a value that makes something go away. All right, so this is 1, 2, 3, 4, 1, 2, 3. So this middle value right here, I'm going to call that 0, because that makes the exponent go away. This that's not very well written. I don't know what letter that was. Let me try this again. Makes the exponent 0. And I center that on my table because that's where the behavior changes. Okay? So on the other side, -1, -2, -3. And on the other side, 1, 2, and 3. And the reason why I want to have the behavior changing point in the middle is I know what's going to happen on either side. All right, so if I was to plug in 0, I get 2 to the power 0. Anything to the power 0 is 1. If I plug in 1, 2 to the power 1 is 2. If I plug in 2, 2 squared is 4. And if I plug in 3, 2 times 2 times 2 is 8. Now, when I have a negative exponent, what's going to happen is, remember, negative exponents flip numbers. So 2 to the -1 becomes 1/2. 2 to the -2, that equals 1/4. And 2 to the -3, that becomes 1/8. So remember, negative exponents flip numbers. And on one side of my behavior changing boundary, my numbers are doubling. 2, 4, 8, 16, 32. On the other side, they're being cut in half because my multiplier, which is 2 over 1, got flipped to 1/2. So this 1 gets cut in half, half gets cut into a fourth, fourth gets cut to an eighth, eighth gets cut to a 16th, 16th gets cut to a 32nd, right? And again, it's very beneficial to know where the behavior changes. All right, let's graph this thing. So 0, 1, 1, 2, 3, 8, there's 5, and there's 8. Right, so you can see over here the height is doubling for every x I go over. For every x I go in the other direction, my height is halving. Okay. And again, this is where the behavior changes. This part of the graph, I have positive exponents. And this part of the graph, I have negative exponents. All right, so I did want to spend a little time reviewing an exponential function before I find the inverse and we start looking at making a table and finding nice points and just kind of reviewing powers of 2. So let me clean all this up and continue with the first goal, and I will be back. I'm back, so let's go ahead and continue with our first goal here. And remember, our first goal is going to be to create a logarithmic function from an exponential function. We just spent a little time reviewing the exponential function. We made a table. We saw what value makes the behavior change. On one side we have positive exponents, and on the other we have negative exponents, flip numbers. And we're going to see that with logarithmic functions as well. So that's why I wanted to review that. But let's continue with our first goal, and that's creating a logarithmic function from an exponential function. Remember, logarithms do one thing. They allow us to isolate an exponent. In this case, for this lesson, we're using it to find an inverse function, but we can also use it to solve equations where the unknown variable is in the exponent. So there's 2 avenues that we use logarithms for, and this is one of them. So let's move forward with our first goal. A review, finding the inverse. So we switch the x and y and we solve for y. And let's review the definition of a logarithm. If a is equal to the b to the c power, then I can isolate the exponent because we use logarithms to isolate exponents. I can rewrite it as c equals log base b of a, and b can't equal 1 and b has to be greater than 0, and that implies that a itself has to be positive as well. All right. So again, I can't stress this enough. We use logarithms to isolate exponents, and that is how we are going to solve for y. So let's go ahead and find the inverse of our exponential function that we began with. And what we're going to do is we're going to switch the x and the y. And we are now left with x equals 2 to the power of y. Now, remember, we want to solve for y, and our y is an exponent, and we need to use a logarithm to isolate the exponent. So we have this, we're going to rewrite it like that, and now I have y is equal to log base 2 of x. Okay, and so to go from here to here, we use the logarithm. So hopefully it made sense how we solved it. Now I want to get into a little bit about what does the inverse mean. And I think that this is a fair question, because if we understand what's actually happening here at the beginning, it makes our second goal much easier to obtain. And our second goal is going to be to find nice points for the logarithm function. So if we're a little bit strategic here, we can make our life a little bit easier. Alrighty. So what does this mean? Okay, so first of all, let's look at this guy. X equals 2 to the power of y. Remember, x is the input, right? This is what we get to plug in. And our output is the y. This is what we get back. So if we are smart with how we pick our values of x, we would get values of x that we've seen in our table. 1, 2, 4, 8, 16, a half, a fourth, an eighth, a 16th, right? Because if we pick values of x that we know are powers of 2, then we have a very easy time getting back values for y. So let me write that down. If we pick x to be powers of 2, right? So we want to play chess, not checkers. We want to think a couple moves ahead. I want to make sure, speaking of that, I don't have to record this again. Make sure I'm on there. Oh, I'm just barely on there, but that's good enough. All right, so we plug in an x value, we get back a y value, right? So, for example, if I plugged in an 8, y would have to be 3, right? You plug in an 8, y has to be 3. That's what the function is. But that's not how we look at it. We look at it in this form. So let's look at the logarithmic version. The log version. The log version here. Y equals log base 2 of x. And let me translate this for you. So, what exponent does y need to be? Or what does y need to be so that when you multiply 2 by itself so many times, you get x? Right, so we pick this, right? This is our input. This is what we get to plug in. This is our input. That's what we plug in. And this is our output, or what we get back, right? So the output is the exponent. What exponent do I need so that 2 becomes that value? What exponent do I need so that 2 becomes that value? What exponent, which is a y, so 2 becomes x. That's how I want you to think about this. Because if we think about it like that, it's going to make it a little bit easier, right? So what I want to do is I want to go through an example of finding nice points for a logarithmic function and hopefully better understand what these represent through this next example. So this is probably a little confusing, which is all right, because we've rewritten an equation that was confusing to begin with because our output is an exponent, right? But again, that's what happens when we're working with the inverse. We switch, and sometimes it makes it a little hard to follow along. So let me clean all this up, come back and get into the second goal, and I'll be back. I'm back for the last time, I promise. So let's go ahead and move forward with the second goal, and that's to find nice points for the logarithmic function and better understand what the input and output represent. Okay? Remember, we get to pick what the input is. We get to do that. That's what's nice. That's how we're going to find nice points. So we want to find nice points for our logarithmic function y equals log base 2 of x, and what exponent, which is the y, what exponent does 2 need to become x? That's how I want you to think about this. What exponent does 2 need to become x? All right, so it would make this a lot easier if we listed the powers of 2. If we know what values we get with specific exponents, then we know what exponent we need, right? So I'm going to start in the middle. 2 to the power 0, that's 1. 2 to the power 2, that's, I'm sorry, we're going to count. 2 to the power 1, that's 2. 2 to the power 2, that's 4. 2 to the power 3, that's 8. And 2 to the power 4, we'll just go to 16. Now, going the other way, remember, when we have negative exponents, we flip these numbers. So 2 over 1 will get flipped, 4 over 1 will get flipped, 8 over 1 will get flipped, and 16 over 1 will get flipped. So 2 to the negative 1, that equals a half. 2 to the negative 2, that equals a fourth. 2 to the negative 3, that equals an eighth. And 2 to the negative 4, that equals a 16th. Forgot to make that a fraction. All right, that equals a 16th. And one day I'm going to write vertically straight and horizontally straight. Excuse me. All right, so we got a lot of information. Okay, and by the way, this side are our x values. All of these guys, these are the x values. We get to pick the x values. And on the other side, the exponents, those are the y values. So, let's start picking values, right? So if y equals log base 2, remember that this is my x, we'll go base 2 of 1. Y equals log base 2 of 1. That means the exponent that I need to turn 2 into 1 is 0. So 0 equals log base 2 of 1. I need a 0 exponent to turn 2 into 1. All right, let's try another one. What if I have, oh, and by the way, here's my ordered pair. 1, 0. Let's find another one. What if I try, I don't know, let's plug in 16. Okay, 16 for x. So I get y equals log base 2 of 16. What exponent do I need so 2 becomes 16? Well, I need an exponent of 4. So that means 4 equals log base 2 of 16. And my ordered pair would become 16, comma 4. Right. Let's do one more with a fraction. What if y equals, I don't know, log base 2 of an 8th? What exponent do I need so that 2 becomes an 8th? I need an exponent of -3. So this would become -3 equals log base 2 of an 8th, which as an ordered pair would become an 8th and -3. Right? So again, the goal of this was to find nice points for the logarithmic function and better understand what the input and output represent. Hopefully I'm achieving that, right? Exponent of 4 makes 2 a 16. An exponent of -3 makes 2 an 8. Okay, so think of it like that. That will help us understand better the logarithmic functions. So I'm going to go ahead and end it here. Your homework assignment is going to be along these lines, but you're going to have to figure a little bit more out than what I've shown. But again, I'm going to go ahead and end it here. I hope everyone is doing all right out there. Have a great day, everybody. Bye-bye.